This video is going to cover the basic wave equations that we talked about in the electromagnetic wave notes. The first thing we have to consider when we're talking about these equations is what each of these variables means. So I'm going to go through each of these and explain a little bit about them and what units they have and how we will use them in this calculation process. So to start off with, the most important variables that we have here are lambda, which actually most people prefer just to write like an upside down y. So it looks something like that. And we have lambda, which equals the wavelength. This is a Greek letter. When we're putting lambda into this equation, it should be measured in meters. So if it's not in meters, we need to convert it to meters to get it to work. The next one I'm going to talk about is the letter nu. It looks like a V, but it's Greek letter nu. This is the frequency. Frequency is the number of times something happens each second. It's measured in hertz. 1 hertz means 1 time per second, or 100 hertz would mean 100 times per second. The last variable that I'm going to talk about here is energy, which is represented by an E. Energy is measured in joules. Hopefully from the past you've done some work with energy. Energy just has to do with the capacity to bring about some sort of change in the physical world or something like that. That's what energy means. So lambda, nu, and E are our 3 variables. In addition to this, we have 2 constants. C is the speed of light. This is 300 million meters per second, or 3.00 times 10 to the 8th meters per second. H is Planck's constant, or Planck's constant. And this one will always be 6.626 times 10 to the negative 34th. Planck's constant is a conversion between energy and frequency. So those two, you don't really have to worry so much about what they mean. Just know that they're constants and that you're going to be plugging them into these equations to figure out other things. All right, we're going to go on to the first example problem here. This problem says, what is the frequency of a wave that has a wavelength of 50.25 centimeters? The first thing I'm going to suggest that you do in these problems is figure out which equation you're going to be using. We're going to be using the C equals lambda nu equation here because this problem involves frequency and wavelength. We want to find the equation that has frequency and wavelength in it, and that is C equals lambda nu, because the lambda is the wavelength and nu is the frequency. So then we write out the problem here is 3 times 10 to the 8th for the speed of light, 3.00 E8. And remember that E means times 10 to the power, so 3.00 E8. I put it this way so that when you put it in your calculator, you can remember to use that notation. It keeps everything together when you put it in the calculator. And we know that this equals our wavelength. Now, something to point out here is that the wavelength was in centimeters, so we need to fix that. If you go through and you do your King Henry died by drinking chocolate milk here, what you can find is that the wavelength actually equals 0.5025 meters. If you want a refresher on that, I recommend you look back at the metric conversion video. That talks all about how we go from one of these units to the other, but the lambda in this case is 0.5025. If you're going to plug wavelength into this equation, it needs to be in meters. So 0.5025 for our lambda, and in this case our nu is what is unknown. We're going to solve this now for nu. And so we know that if we divide both sides by 0.5025, which would be 3.00E8, divided by 0.5025, then we will get nu by itself on the right-hand side of this equation. You put that in your calculator and you should get a larger number. Now, we need to round this to 3 significant figures. What comes out of your calculator is 597014925. And then there's some numbers after the decimal there. If you go back and think about the first unit and what we talked about significant figures, this is kind of a problem because we started off with a couple of numbers here and they definitely didn't have that many significant figures. If you look at the speed of light, that's 3.00 times 10 to the 8th. That has 3 significant figures. If you look at the wavelength, 0.5025 or 0.5025, that has 4 significant figures. We go with the lesser number there, so our answer should have 3 significant figures. If that confuses you, I recommend that you look back at the multiplication division rule in the significant figures notes. You can find a video on that from Unit 1. So we're going to round this number to 3 significant figures. That means starting from the left, we're going to keep the 5, the 9, and the 7, but we're going to round everything after that down. And so all of this here at the end becomes zeros, and we end up with 597 million hertz as our answer. It's hertz because we are talking about frequency here. On to problem number 2. This one says find the wavelength of a wave that has a frequency of 15,000 hertz. Again, here we try and figure out what equation we're going to be using. This has wavelength and it has frequency in it. So again, we're going to be using the equation C equals lambda nu. Plugging in our numbers here, we get 3E8, or I should probably write out here 3.00 E8, just to keep my sig figs intact, equals lambda, this time is our unknown, so we'll leave lambda there, unknown, and then nu is the frequency, and that's 15,000. Solving this for lambda, we are going to divide both sides by 15,000. We get 3.00E8 divided by 15,000, which equals our lambda. And then that lambda, if you go through and you do that calculation, you get 20,000. Now again, we need to consider significant figures. 3.00 times 10 to the 8th has 3 sig figs. The frequency, 15,000, has 2 sig figs. We're going to go with the lesser number there, so our answer should have 2 sig figs. This is a little bit tricky because we have to write this number, which has a bunch of trailing zeros with precisely 2 sig figs. If you remember, that over bar can help us solve this problem. We put a bar over that 1 0, the first one going from the left, and say that one is a known 0 and that it's significant, and the other 3 are insignificant. And now we have 2 significant figures. The last thing we're going to do is throw a unit on this. Lambda is the wavelength, and so it should have units of meters. Now on to problem number 3. In this case, it says how much energy is in a radio wave photon with a frequency of 102.9 megahertz. And then they just tell you that 102.9 megahertz is 102.9 million hertz. They give it to you directly in hertz, so you don't have to do that conversion. This one is talking about energy and frequency. So we need to find an equation up above that has energy and frequency in it. That's going to be this E equals h nu equation. E is energy, h is Planck's constant, and then that nu is frequency. we can just plug in directly here both of these values that we have. Energy is going to be equal to Planck's constant 6.626 times 10 to the negative 34th times that frequency 102900000. We multiply those two together, round to the correct level of significant figures. That's going to be 4 in this case because both Planck's constant and 102.9 have 4 significant figures. And what we get is 6.818 times 10 to the negative 26th. And then the units on energy is joules. This last problem here says, what is the wavelength of a photon with 4.5 times 10 to the negative 19th joules of energy? And then it says to convert it to nanometers. So in this one, we're dealing with wavelength and energy. So we're going to find the equation that has wavelength and energy in it. It is E equals hc over lambda. So this is the equation that we're going to be using on this one. We need to rearrange it a little bit so that it's solved for wavelength. I think that's a little bit easier than just plugging things in right now, because when we're solving for something and it's in the denominator, that can get a little bit tricky. So to try and simplify this and solve it for lambda or wavelength, because that's what we're looking for in this problem, I'm going to start by multiplying both sides by lambda. And so what we get from this is that E lambda equals hc. Now you could just plug it in directly there and it'd be a little bit easier, or you can go all the way and solve completely for lambda. That's what I'm going to do, and I'm going to say lambda then equals hc over E. So now I've just rearranged that equation algebraically to be a little bit better suited for our case here where we're trying to find the wavelength. Now what we're going to do is we're going to start plugging in numbers. So lambda is going to equal h, which is 6.626 times 10 to the negative 34th. Speed of light is 3.00 times 10 to the 8th. And then over the energy, which is 4.5 e negative 19. You plug all of that into your calculator and you should get something very small. We're going to round it to 2 significant figures on this case because the energy only had 2 significant figures. So 0.12345644 joules. Oh, sorry, this is lambda, so that's meters. Be careful about counting your zeros there. Now we need to convert it to nanometers. This is not one of the metric prefixes that I had you learn, but in order to get to nanometers, we're going to have to move the decimal place over 9 spots going to the right. And so if you move it over 9 spots to the right, you get 440 nanometers. So hopefully that has helped you understand the basics of how to use these equations. If you want to see more practice, find the video on the practice worksheet, which has 10 additional problems of this. And if after watching both of these, it doesn't make sense, schedule a time to come in and work with me.